So as a transportation engineer, infrastructure. This is
Oh, is it opening on this screen?
Yep. So this is a project that I'm working on currently right now. It's just an aspect of my project. This road is Mannheim Road. It's right by the airport, the O'Hare International Airport. Right now we're trying to build a bridge that goes over it. So if you're a transportation engineer and building road layout and road design, geometric design is really important. The faster a curve is, the smoother the transition needs to be. If you guys have taken calculus, you'll know that the second, third derivatives, the further down the line you get, the smoother the curve gets. The next drawing that I'm going to show is pavement design.
Oh, you need to zoom in.
Oh my gosh.
Do you want me to navigate it while you talk?
This is so difficult. Oh, yes.
Down there. Is it rotated?
This is sensitive. So these are two cross sections of roads. Basically, as an engineer, you'll want to determine the thickness of it based on the traffic flow that goes over on top of it. This is a typical section of asphalt road. There's a 2-inch layer of wear surface, and then the actual structural supporting portion of the road is underneath it. So if you see construction areas where they're just grinding down just the top 2 inches, that's what they're doing. They're replacing the wear force. So close that. And this is already pulled up, right?
Mm-hmm.
Let's see. Oh, it's Internet Explorer, right?
Yes. How many of you guys are experienced highway drivers?
Bam.
Oh,
All right.
oh, okay.
So
You guys
everyone.
will recognize some of it.
So every once in a while, when you're driving, you'll hit a traffic jam, obviously, but for no apparent reason, there's no accident, no obstruction in the road. All of a sudden, the traffic starts moving freely again. And if you ever wonder why, it's because traffic has memory, and they've set this experiment up. Basically, it's just a big circle with 20 or 25 cars driving around in a circle. If they all wanted to go at the same speed, they can go as fast as they can. But of course, we're human. There's a little delay in our reactions, and certain people drive at different speeds. And this kind of gives you a good showing as why traffic jams happen, even though there's no accidents or obstruction.
So watch. Can you show them the white car?
Yeah. So you'll notice this car slows down just like a half a second. And then you'll notice that these cars stop as well. And then you can see that the car starts stopping, and it actually progresses back into the direction opposite of the traffic. So the traffic jam is here right now. By the end of the video, it'll progress over to here. So if you're driving on the road and all of a sudden slam on the brakes for no apparent reason, there's a saturation traffic. An hour later and 5 miles down the road, you've caused a big traffic jam, even though you may not have realized it. To you, it's only like a second, right? But
That's not funny, no, but can you close the window because it's not going to the video?
oh,
Oh, there's a camera.
that's for later. So that's transportation. Kind of quick trivia: why do passing lanes require less maintenance than the inner lanes? The passing lanes are the lanes on the left-hand side. The inner lanes are the lanes on the right-hand side. Can anyone venture a guess? Yes.
On the right hand side, you typically get them especially on the right-hand side, and you get off on the right-hand side, unless it's a special, they get off on the left, so more people are on the right.
Okay, so volume, that's good, but the majority of the vehicles on the freeways are car traffic, and the reason why the inner lanes require less maintenance is that the inner lanes typically have truck traffic, and the truck traffic causes 99% of the roadway damages. So just kind of, if it's really bumpy, move to the passing lane. It'll be a little less bumpy. As a geotechnical engineer, you're worried about soil, and this is Kansai International Airport. Have you guys, anybody been to Japan before? No? Okay, well, this is a region of Japan called Osaka. So obviously that's Japan, and this area, if it ever clears up. So obviously that island doesn't exist normally. So what Japan, in the early 90s, Japan was running out of space, and they really needed a new airport to sustain their economic development. So what they did was they excavated like an entire mountain and threw it out into the Osaka Bay to build an island specific for this airport facility. And what happened was, so this is a terminal. Terminals are usually, big long structures, so to facilitate all the planes going in, driving out, things like that. So what they had to do was they had to put all this dirt on top of, the seabed, which at that location was a clay layer. If you guys ever take soil engineering or geotechnical engineering when you're in college, clay retains a lot of water, whereas sand, something like sand, doesn't retain very much water. So if you have a bucket of sand and pour water on it, you push down on the sand, the water is going to flow out. Whereas if it's clay, you push down on the clay, it's going to hold its form, and you think you're all good. Only, a year, 5 years later, the water slowly seeps out during that time, and all of a sudden the building that you put on top of that starts to crumble because the soil that you put the building on starts to fall apart. So what they had to do was they had to get as much water out of this clay layer as possible. So they had to drain water out of clay underneath like 80 foot of water, which sounds kind of silly, but that's what they had to do in order to get the structural strength from the clay. And they did this by drilling sand piers all the way down to the next soil layer, and they loaded it by putting dirt on it, and basically they just waited until the water started seeping out. Unfortunately, when they were doing this is the first time anyone has done this. So as much calculations as they took and as much of the safety factors that they put in, it wasn't enough. What had happened was, over the course of 10 years or so, the soil started settling, and when I say settling, it basically means the water started rushing out of underneath it, and the soil started losing its strength and started to go down. And because of that, because the terminal was laid on top of that, what they did was, this was actually kind of ingenious, they built the entire terminal structure on hydraulic jacks. Anyone you guys jacked up a car before? Yeah, so it's basically that for an entire terminal. So like, imagine the school being on hydraulic jacks, and if that corner settles, 3 inches, and this corner settles 1 inch, they were able to jack it up by 3 inches over there and 1 inch over here. And you can see typically what a structural column looks like is the base, kind of cuts off right there, it just anchored into the floor. But because they needed to jack the structure up, they built that jack, and they would slide shims underneath there. The only problem was they blew the calculation by like 2 feet. So they had estimated, over the course of 20 years or so, that the jack they would need, 3 foot of jack or whatever. But it ran out, and the buildings were still settling. So what they had to do was they had to weld 2 extra foot of jack on there so they could still slide shims under there. So geotechnical engineering, really, really important. And probably one of the more difficult engineering topics, but also one of the most interesting. Construction, I kind of want to talk about, this is the first project that I was on when I was out of college back in 2007. Can everybody see all right? So basically this is my project right at the beginning. It was basically a parking lot. This is, I believe, January 2007. We're just doing some boring, checking the soil depths and things like that. February still looks pretty much the same. March, we're getting some equipment in there. You'll notice that on any construction project, we're going to be playing in the dirt for a really, really long time. The caissons go down, like 80, 100 feet. So we're basically, as much as we're building up, we're also building down as well. So this is, I think, did I say March? April, yeah. Yeah, but anyway, so we're doing caisson drilling right now. More caissons. These are sheet piles. You drive sheet piles down to hold back the earth. So that's the mat slab. A mat slab is basically a thick layer of concrete underneath the building to support it. And this is a mat slab being done. These two locations are the locations of the tower cranes that we're going to be putting in. And this is 2 days after the last picture. This was a 10-hour concrete pour. Basically, we would have like 20 trucks at once dumping concrete into this hole. This one took 10 hours. Trump Tower, because of the footprint and the limitation, was a 20-hour pour. So you can't stop. As soon as that first bucket of concrete pours, you got to finish it. So it's from 7 in the morning till 4 in the morning. Got to get it done. After you get done playing the soil, this is the core of the building. The core of the building is basically where it gets its rigidity from. And once you see this start going up, it's going to go up pretty quick. So this was, I believe, in October 2007. Then this would be November. You can see it climbing already. November, I believe this is January. So we've met the street elevation on this side. On the other side, we have not, but the core is already up to floor 6 at that point. You can see the steel structures going up, and we've built the deck up to the second road over there. And then you can see that we've added a lot more steel. I believe this is, at this point, it's probably May. And then, so this is June. This is July. August, and then September they started putting curtain wall on the building, and you can quickly see how fast this goes up once you get out of the ground. And that's why on some of these construction projects, I just like that picture. I think it's okay. But so this is, and we would leave this is where our man hoists are to bring. Huh? I'm sorry, what? One of the parking lots? Oh, yes. Across on the other side of the street, that's where this is. This is south of that parking lot. I know what you're talking about. The ones with the windmills on top. Is that what you're talking about? Yeah, those windmills don't work. I read some of the emails from the back and forth from the developers and the manufacturers. So it was pretty funny. But anyways. And then this was in February. We topped out at the curtain wall. March, we're just doing interior work. This is in May. We took out the hoist to fill it back up with curtain wall, and this is in June at this point. And then just a couple of other pictures for you to see the kind of the progress going around.
Mr. Kuang? Question about working in January with the snow on the ground. Like, does the cold really hold up any of the construction?
So what you do is you want to time it so that you're doing the interior trades in January, and even though there's no heat, what we do is we rent temporary heaters. It's basically what I would call a cauldron of fire. It's basically something this long and about this wide, and there's a literal flame in there that shoots out. So you have one unit in there, and like an entire gym will be like 80 degrees. So that's what we do. We got to keep the warm for health, safety reasons, and if there's if we're doing concrete pour, we have to do that under certain temperatures. So we have to maintain that if we're doing that outside. We put like mats on top or whatever. So that's that. If there's time at the end, I'll run through my current project. But structural engineering. So this is a picture that I took on the way in this morning. How many of you guys know what an I-beam is? All right, good. So that's an I-beam. The sophomores didn't know. So basically, what an I-beam does is it resists the force in one particular direction. In this location, the primary force that's acting on it is gravity, and anything that's on top of that. So that's why it's located, it's standing up vertical rather than being on its side. When you do something like that, it's the amount of mass that's farther away from the center that helps resist that load. So if you take something like a ruler. Okay, yeah. So which way do you think it would be easier to break this? Like this or like that?
The first way.
Yeah, like this, right? Because the reason why is, mathematically, most of the mass is very close to the center of when you put the force down. When you're like this, not only are you pushing through all this mass, the bottom's got to contract and the top's got to stretch in order for it to break. So that's the same thing here, only we're putting a lot more mass on either side. But I really need 2 volunteers right now. All right, you. And I need somebody who thinks they're the strongest person in this room right now. All right, you back there. Oh. All right.
Sorry,
So basically,
what'd I do? Stuck up his middle finger. Oh, it's probably my index finger.
So what I'm going to ask you guys to do is, I'm going to ask you guys to hold a bunch of textbooks for as long as possible.
I bet Peter's strong.
Okay. So with that said, who do you think would be able to carry the books the
Peter.
longest? All right,
Well, are you sure you want to put yourself up to that?
all right, can you stand here for a second? All right, put your legs forward like this.
Carry bases.
Face that way. Hold your hand like this. Put your elbows together and make sure that your elbows is touching your abdomen. All right.
Looks comfortable.
It's not.
It's not meant to be comfortable. All right, hold that. Now for you, stand here next to me. Put your legs out as wide as possible, and stick your arms straight out. All right. Mr. Muscle's here. With that said, hey now. With that said, now who do you think could hold the weight the longest?
Peter.
All right. Well. All right. Well, anyways.
Should we add more?
I want to have them stand there for a little bit. I want to go through the next activity. Could you guys combine groups really quick?
These
Those
two?
two? Yep.
Okay.
And what I'm going to do is I am going to ask you to be building a structure out of 4 pieces of paper.
Obviously, just my one.
How you doing over there?
Okay.
You're okay? All right, good. So basically what I want you to do is I'm going to show you one that I did. And you okay?
Yeah.
All right.
It's a good workout. Strength training.
Yeah, straight
Yeah,
line,
throw
right?
some weight machine. Hey, don't touch me.
How you doing? You good?
Kenneth.
You think you can handle another book?
Leave him alone.
Put another book over there? And since he's got one extra,
Hey, get away.
I might as well put one on yours, right? All right. Okay, good.
Now he good.
So
That's
basically,
impressive, Taylor.
what'd you say?
Oh, do you have your old pieces of paper?
Yeah, they are.
I have my.
It's hard to hold. Like my legs are like this too.
Just now?
Stand your legs.
Oh, here.
Hang on.
In here.
Oh, you got it?
Hey,
All right.
don't talk like that.
How you doing?
Yeah, it's hard.
I'll take him.
All right. I think we got the point, all right? I'm sure you could have probably held on to that for a little longer, but...
Yeah.
Thanks. Let's give him a round of applause.
Good
Good
job,
work,
Peter.
guys. Good work.
Good job, Peter.
Do you mind joining this group?